Section 6.2 Determine the four characteristics of an association. Section 6.1 we already talked about the scatterplot, the linear correlation. We have the positive linear correlation or negative linear correlation. And for these sessions, we'll be focusing on the linear correlation again, but this time we need to know how to find out the strength of the association. Shape of an association. If the points of a scatterplot lie close to or on a line, we say the variables are linear associated, and that is a linear association, or we could say linear correlation. So this is my scatterplot in here. If I could draw a straight line here, and all those points is going to be around the straight line. So we believe there is a linear correlation. And also, we talk about it on the section 6.1. Since the slope is increasing here, so we know there is a positively linear correlation. If we have the picture, the points go anywhere. You can't draw a line on it. Means like there is non-linear correlation. Okay, that's a non-linear correlation. Okay, let's look at more of the pictures in here. The first one here, all those points is going on like this direction, and I could easily draw a line on it. And for this line, this is decreasing, right? The slope is decreasing. So we know this is going to be negative linear correlation. And for this one, I could draw a line on it, and all the points is going to be around the straight line. And the slope is positive. So we know this is positive linear correlation. And this picture, that's a no pattern at all. I can't draw a straight line from anywhere. So we call this as no correlation. Okay, no correlation. And then for the last one, I can't draw a line in this picture, but you guys can see that we do have some patterns on it. Right, this is looks like the parabola. We do have the pattern, and we can't draw a straight line on here, so we only can draw the conclusion saying that there is non-linear correlation. Okay, you can't say no correlation for this picture because they may have other kinds of correlation, but just not the linear one. Right now for these two sessions, we only focus for the linear correlation. So when you guys look at the scatterplot, they do have some pattern. You only can say there is nonlinear correlation. You can't put no correlation. Unless you see the picture is like no patterns at all, you can't draw the straight line on here. So you could draw the conclusion, say no correlation. Strength of an association. If a curve passes through all the points on a scatterplot, we say that there is exact association with respect to the curve. So look at the pictures in here. This is my scatterplot, but you could see I could draw a straight line on it, and all the points is gonna be on my straight line. Okay, so we say this is gonna be the perfect linear correlation. And since this is a negative slope, the slope is decreasing, so we could say there is a negatively perfect linear correlation. And for the second one, you could see the points is going like here. Okay, I could draw a straight line in here also. And all those points is really close to my straight line. So we could say there is a strong association, or there's a strong correlation. And then for the last one, you may not see any patterns from here, right? You may say there is a no correlation, but actually, look at the scatterplot is very subjective. Later on, we're gonna learn how to find the correlation coefficients to determine how strength of an association. Okay, look at this example. The figure shows a scatterplot comparing carbohydrates and calories for 29 pieces made by 6 of the leading pizza companies. So we do have the scatterplots in here, okay? And this is related to the carbohydrates and the calories. For example, if you have the pizza, the carbohydrates is about 20 grams, that means this pizza will be 250 calories. And remember, we learned it from the session 6.1. When our x-axis here, this is called the explanatory variable. And for the y-axis, this is a response variable. So that means like how much calories you're gonna consume, it all depends on how many carbohydrates that you have in here. And then we have the second one, carbohydrates with the fat in here. And again, on your x-axis, this is a carbohydrates, and for the y-axis, this is going to be the fat. For example, if I have a 20 gram of carbohydrates, I do have 50 gram of fat. It depends on the pizza, okay, made by which pizza companies. Okay, look at the example. For each of the scatterplots, describe the shape of the association. So obviously, these two pictures, there is a linear correlation. And we need to describe the shape of the association. So all those points is going on like this direction, and I could draw the lines on it. So we will say for both scatterplots, the points lines near in line. So the associations are both linear. Okay, number 2, compare the strength of two associations. So after I draw the straight lines on here, you can see for the first picture here, all the points is really close to my straight line. And for the second one, some of the points are kind of far away from the straight lines in here. So when we compare with these two associations, we're gonna say the points in the first scatterplot lie closer to the line than the points in the second one. So the association between the carbohydrates and calories is stronger than the association between carbohydrates and fat. Number 3, for each of the scatterplots, identify whether the association is positive, negative, or neither. So both of the picture, the straight line is going to be increasing. So means like they do have a positive slope in here. So we know that is a positive linear correlation, or you could say the associations are both positive. Number 4, estimate the caloric content of the pizza with 53 grams of carbohydrates. So 53 grams, so somewhere like here, right? So we want to go up. When we hit the points, go to the left, we're gonna see this is about like 500 gram calories. Try to do the number 5. Same idea. Estimate the fat content of the pizza with 53 grams of carbohydrates. So 53 grams somewhere like here, going up to the point, go to the left. You're gonna see this is gonna be 21 here. Properties of the linear correlation coefficient. Assume R is the linear correlation coefficient for the association between two numerical variables. So what is a R? R is for you guys to measure the strength of the linear correlation. Remember, when we look at the scatterplots, if all the points really close to the straight line, we may say that is a strong linear correlation. If all those points is going to be kind of far away from the straight line, we may say that is a weak linear correlation. But look at the scatter plot is really subjective. So what we're going to do, we want to find out the R. And the R here is called linear correlation coefficients. This is tell you guys how the strength of the linear correlation in here. So look at some properties. First, R is always in between -1 and 1. So R is always in between here, -1 to 1. If the R is positive, then the variables are positively associated. So if you find out the R is going to be greater than 0, is a positive number, then we know this is going to be positive correlation. Means like the pictures is going to be go on like increasing. Okay, go on like this way. If you find your R is negative, then the variables are negatively associated. So if you find out the R is going to be the negative number less than the 0, that means the slope is going to be decreasing. Okay, slope is decreasing. If the R equal to 0, R equal to 0 at this point means there is no linear association. Okay, no linear correlation. But keep in mind that even though if you find your R equal to 0, you only can draw the conclusion saying that there's a no linear association. You can't say there's a no correlation because we may have some other patterns on the scatter plot. We may have some other kinds of correlation. It's just not the linear one. Okay, more properties of the linear correlation coefficient. The larger the value of R, the stronger the linear association will be. So look at this picture. If R equal to 1, R equal to 1 in here, then the points lie exactly on a line and the association is positive. So when you have all the points on the straight line, you will find your R equal to 1. And recall there is a positive perfect association. If your R equal to -1, at this point, means all the points lying exactly on the line. And the association is going to be negative. So we say this is a perfect negative linear correlation. And if your R is really close to the +1 here, we're going to say there is a strong positive linear correlation. Or if you are close to -1 in here, we're going to say there is a strong negative linear correlation. But if your R is really close to the 0, we will say there is a weak linear correlation. So you could see this is going to be perfect when your R equal to +1 or -1. If you are close to the +1 or -1, we're going to call that is a strong linear correlation. But if you are really close to the 0 in here, then we say there is a weak linear correlation. If your R equal to the 0, R equal to the 0, that is a nonlinear correlation. Okay, let's look at more example for the correlation coefficient R. So the first picture in here, you can see I could draw a straight line on it, and all the points is going to be exactly on my straight line. And the slope is going to be positive. So if we use the data to find out the R, you will find the R equal to 1. And we call this as a perfect positive correlation. Second picture is here. I still can draw the straight line in here, and all the points is really close to my straight line. My slope is positive. So when we use the data to find the R, we will find the R equal to 0.81. 0.81, which is really close to the positive one. So we say there is a strong positive correlation. This one, you didn't see any patterns from here, but actually you could draw the straight line on like this direction. But compare with the picture 2 here, the points is kind of far away from the straight line. So when we find the R, we only find the R equal to 0.45. 0.45, which is less than 0.5, that means it close to the 0. We could say that is a weak positive correlation. Okay, this one. Again, we could draw the straight line on it. All the points is exactly on my straight line. And the direction is going to be decreasing. So this is called perfect negative correlation, and R equal to -1. And this one, when I draw the straight line, the points is really close to my line in here. And when you use the data to find the R, that will be equal to -0.92. And -0.92, which is really close to the -1. So we say there is a strong negative correlation. Okay, last one. You didn't see any patterns at all, right? So if we use the data to find the R, you're gonna see the R will be equal to 0.04. 0.04 is really close to the 0. And that's a no pattern at all. So we're gonna say this is a no correlation. And it is important to remember that if R close to 0, it does not mean that there's a no relation between x and y. Just that there is no linear correlation. Okay, they may have some other types of correlation, it's just not the linear one. Okay, order of determining the 4 characteristics of an association. We determine the 4 characteristics of an association in the following order. Number 1, identify all outliers. Remember what is the outliers? If you have the points far away from the majority, we consider that's an outlier. If you find it, your data has an outlier, you may need to double check to your data. Did you make any mistake when you inputting the data or any mistake for the measurement? Correct the errors if possible. If the errors cannot be corrected, remove the outliers. Okay, we may want to take it out. And for other outliers, determine whether they should be analyzed in a separate study. For like those removed outliers, we may want to consider to analysis in another study. Number 2, determine the shape of the association. So you may want to see if there's a linear correlation or other kinds of correlation. Number 3, if the shape is linear, then on the basis of R and the scatterplot, determine the strength. If you believe there's a linear correlation, you want to find out the R and look at the scatterplot. Make sure they have the strong or weak or perfect linear correlation. And if the shape is non-linear, then on the basis of the scatterplot, determine the strength. Number 4, determine the direction. So if you know there's a linear correlation, you want to find it out, it should be positive or negative, or neither. Okay, find the correlation coefficient R. The linear correlation coefficient R measures the strength of a linear relationship between the pair values in a sample. You can find the R using the formula or calculator. To use the formula to find the R is really complicated. I'm not going to teach you guys for this class. But if you guys take the 227 later on, you will need to know how to find the R using the formula. And for this class, I'm only asking you guys use the calculator to find the R. And you guys need the graphic calculator to find the R in here. And this is the instruction how to use the TI-84 plus and 83 plus to find the linear correlation coefficient R. If you don't have the calculator, you could use the online graphic calculator. So I will use another example to teach you guys how to find your R in here. Look at this example. Some order pairs are shown in the table below. Let x be the explanatory variables and the y will be the response variable. So we have the table in here. We have the coordinate here, 1, 2, 3, 6, 4, 4, 6, 8, 7, and 10. First, construct a scatterplot. Okay, so your x is an explanatory variable, y will be the response variable. First coordinate, 1 and 2, x equal to 1, y equal to 2. Second coordinate, 3 and 6. So I have a 3 here, 6 in here. And then 4, 4, 6, 8, and 7, 10. So just do it one by hand, construct the scatterplot. Okay, B. Is there a linear association, nonlinear association, or no association? So you could see I could draw the straight line in here, right? And the points is going to be close to my straight line. So we believe that there is a linear association. Okay, C, compute the R. So here we need to use your calculator. So you will have your calculator here. This is a similar to your TI-83 or TI-84 plus. So first, we need to input the data. So we're gonna click on the stat, find out the stat on your calculator. You're gonna see that's a number 1 added. So click on number 1. On the L1, we're gonna plug in for my x in here. So 1, enter, 3, enter, 4, enter, 6, enter, 7, enter. And for the L2, we're gonna do it one by one also. 2, enter, 6, enter, 4, enter, 8, enter, 10, enter. Okay, one more time. Click on the stat, click on number 1 added. For the L1, plug in the data for your x. L2, plug in the data on your y in here. Okay, now click on the stat again. You're gonna use the arrow button, go to the right, go to the test. And then we're gonna go up. You're gonna find the linear regression t-test. Okay, linear regression t-test. Enter. So my data is already on my L1. Okay, if you plug into the L3 or L4, you could change it. You could just do second 1, that's for L1. And then enter. For the Y data, that's on your L2. So second 2, enter, that's on L2. The frequency, just keep it as a 1 in here. Okay, for the next one, this is related to the hypothesis testing. You guys gonna learn it from the Math 227. Right now, I just want you guys remember that you want to choose the not equal to 0. Okay, not equal to 0, and then enter. Or go down, use the arrow button, go down. The regression equation, leave it as blank. Go to calculate. Okay, enter. You could see this screen, and then you're gonna scroll down. Go down here, you're gonna find out your R. R equal to 0.927. Okay, compute your R. 1 to 3 decimal space, 0.927. Okay, write it down in here. And make sure that you guys need to know how to find your R on the exam. Okay, D. On the basis of the scatterplot and R, determine the strength of the association. So when R equal to 0.927, we consider this is gonna be perfect, strong, or weak, or even no linear correlation. That is a strong linear correlation, right? Because 0.9 is really close to the positive one. And also, we could see the direction here, the slope is increasing. So we know this is gonna be the positive, strong linear correlation. Okay, looking variable. A looking variable is a variable that causes both the explanatory and the response variable to change during the study. We talked about this guy on the chapter 2 already, and right now I'm gonna give you guys another example. What's a looking variable? Okay, for example, there is a correlation between shark attacks and ice cream sales. Both of them increase at the same time. So think about like these two events. I have two variables in here, shark attacks and the ice cream sales. Do they relate to each other? You could say, oh, well, this is two events, it seems like it's unrelated, right? But how can they link up with each other? So since we know that shark attacks and the ice cream events are two different events, so we may consider that we do have the looking variables in between. And when we say there is a correlation, how can you explain like this correlation? Either more people buying ice cream cause shark to attack, or shark attacks cause people to buy more ice cream? The answer is neither, okay? Remember, correlation does not imply causation. There is a correlation between the shark attacks and the ice cream sales. It doesn't mean one thing's caused to another thing to happen. So the answer for this question here is gonna be neither. Okay, they have a relationship but doesn't imply the causation. So for this example, we're gonna say the looking variable is gonna be the weather. As the weather goes warmer, more people buy ice cream and more people go to the beach. So if more people buy ice cream, they will have ice cream sales. And more people go to the beach, there will be higher chance to get more shark attacks. So we say that's a correlation. But here, I want you guys to remember that correlation does not imply causation. That's a correlation doesn't mean one thing's cause and other things to happen. And in this example, looking variable will be the weather. Okay, this is the looking variable. Okay, the scatterplot compares the score of test 4 and test 5 for a calculus course taught by the author. Describe the four characteristics of the association. So first, let's draw the straight line on here. And then, look at the pictures here. I want you guys to find it out. Do we have any outliers in here? Remember what's an outlier? Outlier means one or 2 points is going to be far away from the majority. No, right? All those points is kind of around the straight line in here. So we know that is a no outliers. Okay, second, look at the shape. Do they have any association? Do they have a linear association or other type of association or no association? All these points is going to be close to the straight line here. So the association should be linear. So write down these two first. First, we don't have outliers. Second, there is a linear association because all the points is going to be around the straight line. Okay, the strength. How strong of the linear correlation? Will it be perfect, strong, or weak, or even no linear correlation? The points is kind of like really close to the line here, so we believe that there is a strong linear correlation. And actually, if you got like the data, use this data to find the R, you could find the R is going to be 0.81. And which is 0.81 is really close to the one in here. So we know there is a strong linear correlation. Okay, last one, the direction. What is the linear correlation? Is it positive or negative or neither? This is going to be the positive, right? Since the slope is increasing. And we find the R is positive 0.81. So you know this is going to be positive association. Means when the test 4 points is increasing, the test 5 points is also increasing. Number 2, does a higher score on test 4 cause a higher score on test 5? If no, describe at least one possible looking variable. Okay, so a student's score on test 4 does not directly affect the student's score on test 5. There are many possible looking variables. Okay, the variables may be affect the result on this example, including student study habit, the consistency in the level of difficulty of the test, and test 4 impact on the student's motivation and confidence. The extent to which test 5 concept build on the test 4, and the student's strength in the algebra, which is useful tool in calculus. So we may have a lot of the looking variable and affect the student's scores on test 5. That's it for the session 6.2.